In this video, I show you how to graph equations expressed in polar coordinates. It's often useful to know how to sketch the graph of an equation expressed in polar coordinates in the xy plane. One way is to just plot points. This is very useful if the radius is already a function of the angle. You then just pick a list of angle values and find the corresponding radii and plot them in order, in increasing order of the angle. And then from there, once you plot all the points, you simply just connect the curves and hope that you're right. Obviously, we need a more refined technique. So one thing you can do is to do a test for symmetry. Now there's a x-axis, y-axis, and origin symmetry, but here we call it the axis with respect to the line theta equals pi over 2. That's the y-axis symmetry. You have the pole symmetry, that's the origin. And you have the polar ray symmetry, which is the x-axis symmetry. In each case, there's a test corresponding to what point would be on the graph if it had that type of symmetry. So assuming that you started with the point r comma theta, if you had polar axis symmetry, then the point r comma negative theta should also be on the graph. If you started with the point r comma theta and you had theta equals pi over 2 symmetry, y-axis symmetry, well, that would mean then negative r comma negative theta would be a point in the graph. So the point r comma negative theta, it does not need to satisfy the equation if r comma theta does, because for every single point, there's many representations of it. So we'll often use alternate tests, which are all found by remembering that if r comma theta is on the graph, then another representation of that point is negative r comma theta plus pi. Also, it's useful to remember that if a graph possesses two types of symmetry, it automatically possesses all three. So if your graph passes two of these tests, the other one comes automatically. And if it fails any one, then it can never have two. It can only ever have none or one. As an example, I'll test for symmetry for the following problems. I'll show that the graph of r equals 4 times the cosine of theta is symmetric with respect to the polar axis. To do so, I'll use one of the two tests. Now, the black one I consider the primary test. I'll replace r with r, which means I don't do anything, and I'll replace theta with negative theta. The logic goes like this. We assume that r comma negative theta is on the graph. Now, if that's true, that means that equation must be true. But if that's true, remember cosine's even, then that equation is true. But if that equation is true, then r comma theta is on the graph. Also notice that these steps are reversible. So then if r comma theta is on the graph, then r comma negative theta is on the graph. Now I'll show that the graph of r equals sine squared of theta is symmetric with respect to the y-axis. Theta equals pi over 2. To do that, I'll try the primary test first. I'll just replace the r with negative r, the theta with the negative theta. By doing so, though, and then simplifying, you get negative r equals sine squared of theta. I didn't get the equation that I want to start with back. So then it appears that this graph would not be symmetric with respect to the line theta equals pi over 2. But that's only one version of the test. Let's try the other. If you try r is replaced with r and theta is replaced with pi minus theta, then I get this will be on the graph. That would imply this equation has to be true. But I know by the different angle formula for sine that that's the same as just that. And that implies that r comma theta is on the graph also. So if r comma theta is on the graph, then r comma pi minus theta is on the graph, and vice versa, because these steps are also reversible. That means that this graph is symmetric with respect to the y-axis, or theta equals pi over 2. Since our polar graph and coordinates have been superimposed over the Cartesian plane, that means that the curve would have slopes at different points. So it might be nice to know what that slope is. So assume then that r is a differentiable function in terms of theta. If we use the formula that y is in terms of r and theta and x in terms of r and theta, just using what we learned from trigonometry, then y and x are both functions of the parameter theta. And therefore, we can find the derivative of y in terms of x by just treating it like the derivative of a curve defined parametrically in terms of theta. So we take the derivative of the y in terms of theta, we take the derivative of the x in terms of theta, and we get this formula. Now you can memorize the result, or you can just remember the derivation of the formula and rely upon our results from parametric equations instead. I myself remember how to derive it. I don't memorize the formula. So if I want to know at what points will this curve have a horizontal tangent, I would need to know the slope everywhere. So to find the slope, dy dx, I've included the formula for you. So all we need to do is compute then what is dr d theta. And in this case, that would be a -2 times the sine of theta. So dy dx should equal the derivative of r in terms of theta, -2 sine of theta multiplied to the sine of theta. And to that I'm adding r, which is 2 times the cosine of theta, multiplied by the cosine of theta. And that's all over, or divided by, the derivative, which was -2 sine of theta, being multiplied to the cosine of theta. And then to that I subtract the r, which was 2 times the cosine of theta, and I multiply by the sine of theta. Now you'll notice that this can be simplified to be, at least in the numerator, you get 2 times the cosine squared of theta minus the sine squared of theta, while in the denominator, if you take out the -1, well, that doesn't really matter, I guess. If you just combine them, you would get a -4 sine of theta cosine of theta. The numerator then can be condensed, if you liked, into 2 times the cosine of 2 theta using the double angle formula. And the denominator can actually also be condensed into -2 times the sine of 2 theta. So that is the cosine of 2 theta over the sine of 2 theta. And that further reduces to just the cotangent. Oh, actually there's a negative there. -1 there. -1 there. Negative cotangent of 2 theta. So I'd like to know when this is 0, because that's how I get a horizontal tangent line. So this is 0 then whenever the angle for the cotangent is pi over 2 or 3 pi over 2. So if the angle 2 theta happened to equal to pi over 2, that's when theta is pi over 4. That's when I would have a horizontal tangent. Also, if the angle was 3 pi over 2, then the angle would be pi over 3 pi over 4. That's another place where this angle, this particular thing, would then have a horizontal tangent line. For those two angles, then I can find for you the different points. Because we know the x-coordinate, we know the y-coordinate. Remember, the x-coordinate is r times the cosine of theta, and y is r times the sine of theta. So in our case, if I had picked only, if I look only at pi over 4, that point would have an x-coordinate, which would be the r, 2 times the cosine of pi over 4, times the cosine of pi over 4. And the cosine of pi over 4, that's the square root of 2 over 2. And because there's 2 cosines, I'm squaring it. That's 1 over 2. That's just 1. While the y-coordinate would then be r, which is 2 times the cosine of pi over 4, times the sine of pi over 4. And for the same reasons, that's actually 1 also. So at the point 1, 1 in Cartesian coordinates, that would then be a point on the graph where you have a horizontal tangent line. If you'd rather express the answer in terms of polar coordinates, you could, because you have the angle after all, and you have the radius. You could just use that instead. And I'll leave the other point for you. But the real reason that we usually teach this formula is that it's very useful to describe the tangent line at some very special points. Assume that you're at the pole. That means that the r is 0, and the angle could be whatever it likes. So we'll say the theta is alpha. But the rate of change of the radius as the angle changes is just not 0. If you look at the slope of the line, our graph, at that point where the radius is 0 and the angle is alpha, you can use this formula to find out what that slope would be. But by just plugging in theta equals alpha, you would then get this formula. Remember, the r is 0 at this angle. But that would then mean the upper portion would cancel and the lower portion would partly cancel. And since the rate of change of the radius with respect to the angle is not 0, those factors would cancel. In the end, just giving us the sine of the alpha over cosine of alpha. And that's the tangent of alpha. But if r is 0, that means in Cartesian coordinates, that means we're at the point 0, 0 in x and y coordinates. So we know how to find the equation of a line, though, whose slope is tangent of alpha at the point 0, 0. That's it right there. But if you convert this back into polar form, that's actually theta equals alpha in terms of just Cartesian coordinates. So y equals the tangent of alpha times x is the Cartesian coordinate form of the polar equation theta equals alpha. That means then that if you plot the point 0, alpha and you draw on the line theta equals alpha, then as your angle increases, your graph will use the line theta equals alpha as the tangent line to the point as you get near the pole. Just doing that again, if this time we assume that the radius has reached a non-zero relative extrema, max, min, for some angle theta equals alpha, that would then mean that the derivative of the radius in terms of the angle would be 0, assuming that the derivative of course exists. But then we could find the slope at that point by just using the formula, because the rate of change of the y in terms of x is given by this formula. But if we plug in that theta equals alpha, then this time the derivative of r in terms of theta would be 0 at that angle. And since the radius is non-zero, then actually quite a bit is cancels, giving you this time -1 over the tangent of alpha. But if you remember though, if you're at the origin, the line whose slope is tangent of alpha is given by y equals the tangent of alpha times x. But that means that line and the tangent line to the curve are perpendicular at that time, because see, their slopes are negative reciprocals. So that means then that if you draw the angle theta equals alpha, when you're at the maximum, if you're looking at a relative maximum in the radius, or a relative minimum in the radius, for some positive radius, then as you draw the curve and rotate into it, the tangent line will be perpendicular to the angle. Well, that means then as the angle increases and you draw your curve, that the curve will get a tangent line that is perpendicular to the line theta equals alpha. So for example, if you consider the rose curve, r equals 3 times the cosine of 3 theta, then if you look at it when the angle is 0, the radius has reached a maximum value. And in fact, the rate of change of the radius in terms of theta is 0. So the tangent line must be perpendicular to the line theta equals 0 at that point. As you can see, it clearly is. On the other hand, when you look at the angle pi over 6, the graph comes to the pole. But once again, the rate of change of the radius in terms of theta this time is not 0, as you're still moving. And therefore, if you draw the line theta equals pi over 6, then that line is the tangent line to the curve. To use all these sort of together, it's very useful to draw your equation in an r theta Cartesian plane so that the horizontal axis is theta and the vertical axis is r, or r squared. So for example, what if I wanted to go and sketch the graph r squared equals the sine of 2 theta in the polar plane? I would first draw the graph in the theta r squared plane. That way I can look at r squared values instead. That gives you just the normal sine graph. But if you then take this equation and take its square root, anywhere r squared would then be negative. The square root of that is just not going to exist, so there would be no graph in this range or in this range. But when you take the square root, for every positive result, there's also going to be a negative result, and that will give you this picture right here. This is the graph of the two different branches put together, both when you look at the positive and the negative branch of the square root. So the way you use that is, as the angle here increases, notice what happens with the radius. So here, for the angle to increase, you're going counterclockwise. So in the beginning, as the radius increases, as the angle increases, the radius increases. So you are spiraling away from the origin. Also notice that when you're at this angle, it looks like it's pi over 4, you have reached a place where the radius has reached a relative maximum. That means that if you draw on that angle, theta equals pi over 4 right here, we should see that the graph, its tangent line is perpendicular to that line, and it certainly appears to be so. But it looks like pi over 2 from pi over 4 to pi over 2, the radius then decreases in time. As it decreases, that means you must be coming back to the origin. So this curve will, in the beginning, rotate outwards and then rotate back inwards. It must start at radius 0, go to radius 1, and come back to radius 0 in the angle range from 0 to pi over 2. But then, because this has an exact mirror image below, that means that for this curve, there has to be a mirror image exactly, in this case with respect to the origin, because I'm changing the radius from whatever it was to its negation. I'm keeping the angle so that the points in the end must exhibit polar the pole symmetry, because the angle is the same and the radii are different. And that gives you a basic introduction to how to graph equations expressed in polar coordinates.